Assalamualaikum and very good morning class. Our topic starting this week is on Fourier transform. In this PowerPoint, we will discuss on the comparison between periodic and non-periodic signals, comparison between Fourier series and Fourier transform, and finally the introduction on Fourier transform, which include its definition. Now let us review on periodic and non-periodic signals. Before we proceed with Fourier transform, let us recap our topics on Fourier series. We start with review on trigonometric Fourier series for periodic waveforms. As we know, if signal ft is periodic with period t, then ft can be expressed as a trigonometric Fourier series, which is ft equal to a0 plus a1 cos t plus a2 cos 2t plus a3 cos 3t plus triple dot plus b1 sin t plus b2 sin 2t plus b3 sin 3t plus triple dot, and we name it as equation 0. The coefficients a0, an and bn can be determined using the equation provided in the slide. Exponential Fourier series, on the other hand, is the exponential form that allows us to approximate a periodic signal to any degree of accuracy by adding a sufficient number of complex exponential functions as given in the following in the first line, where the coefficients can be calculated using the given equation. Finally, the exponential series will be the expansion of the exponential series is given on the last line. Generally, the exponential Fourier series for periodic waveform can be expressed as the equation ft equal to summation of n from minus infinity to infinity coefficient cn times exponential e to the power j n omega t, where we can find the coefficient cn using the formula given here, and where Cn will include Cn as well as C minus n. And if we expand the exponential Fourier series, it will be both in the negative values as well as in the positive values, as shown here in the equations at the bottom of the slide. Most of the signals that we're dealing with previously were periodic signals. Now let us look at the difference between periodic and non-periodic, or also called aperiodic waveform. A signal which repeats itself after a specific interval of time is called periodic signal. Periodic signal is a signal that repeats its pattern over a period. It can be represented by a mathematical equation, and their value can be determined at any point of times. Periodic signals are deterministic signals, and the examples of periodic signals are such as sine, cosine, square, sawtooth waveforms. The figures show examples of a periodic signal. Whereas a signal which does not repeat itself after a specific interval of time is a non-periodic signal. The signal does not repeat its patterns over a period, and it cannot be represented by a mathematical equation. Their value cannot be determined with certainty at any point of time, and non-periodic signals are random signals. Examples of non-periodic signals are sound signals from radio and also all types of noise. The figure below shows one example of a non-periodic signal. But periodicity is too limited in real applications. Therefore, sometimes we were dealing with a periodic signal in which we use Fourier transform. The reason is that signals used in communication system are not periodic, and it is said they are aperiodic. Since we were dealing a lot with exponential in Fourier series, let us recap the relationship between exponential and sinusoids. Euler's formula, named after Leonhard Euler, is a mathematical formula in complex analysis that establishes the fundamental relationship between the trigonometric functions and the complex exponential function. Euler's formula states that for any real number x, exponential ej omega t equal cos omega t plus j sine omega t, and e to the power of minus j omega t equal cos bracket minus omega t plus j sine bracket minus omega t. And if we rewrite the equation for the minus and exponential, we have e minus j omega t equal cos omega t minus j sine omega t. And the relationship between the sinusoids and exponential is given in the formula for sine and cosine omega t. In signal analysis, frequency to be omega in exponential e j omega t. The previous slide shows that Euler's equation provides the link between exponential e j omega t and the sine cosine functions. What is the physical interpretation of the exponential term e j omega t? Okay, if you look at the diagram below, regard this as a vector with unit magnitude rotating in a complex plane at a rate of omega radian per second in the direction shown in figure. Unity vector because the magnitude of the vector is ej omega magnitude is 1. Cos omega t and sin omega t are the projection of this vector on the real axis x-axis and imaginary axis y-axis in this diagram. Before we proceed with Fourier transform, let us take a look at the difference between Fourier series and Fourier transform. As demonstrated in previous chapter, Fourier series is a representation of a function into sum of sines and cosines when multiplied with a certain weight, or we call it coefficient. The periodic signals can be broken into further signals with the following properties. The signals are sine and cosine. The signals are harmonics of each other. The figure shows the left-hand side is the figure in time domain ft time over t, and the second figure is the Fourier series frequency versus f omega versus omega. On the other hand, Fourier transform states that the non-periodic signals whose area under the curve is finite can also be represented into integrals of sines and cosines after being multiplied by a certain weight. A non-periodic signal is transformed from time domain into frequency domain not in the form of series but as a weighted integral transform as demonstrated in the figure on the slide. Okay, this is the time domain and this is the frequency domain after we do the Fourier transform. Fourier series and Fourier transform. Fourier transform is a mathematical method to convert a function amplitude versus time domain to amplitude versus frequency domain. It is same as what Fourier series did, but Fourier series is for periodic function, whereas Fourier transform is for non-periodic function. Fourier transform is actually more physically real because any real world signal must have finite energy and must therefore be aperiodic. Fourier series is applicable only to periodic signals which has infinite signal energy. If we look at the diagram here, we can conclude that Fourier series of periodic square wave is equivalent to Fourier series sinc function of a spectrum, and it is discrete. Fourier transform is a single pulse of square wave, and when it is transformed, the Fourier transform will have same sinc function but continuous. A time domain analysis is an analysis of physical signals, mathematical functions, or time series of data in reference to time. Also, in time domain, the signal or function's value is understood for all real numbers at various separate instances in the case of discrete time or continuous time. Furthermore, an oscilloscope is a tool commonly used in the laboratory to see real-world signals in a time domain. A time domain graph can show how a signal changes with time, whereas a frequency domain graph will show how much of the signal lies within each given frequency band over a range of frequency. Frequency domain displays how much of the signal exists within a given frequency band concerning a range of frequency. Also, a frequency domain representation can include information on the phase shift that must be applied to each sinusoidal to be able to recombine the frequency components to recover the original signal. This is when we talk about application. We can convert a designated signal or function between a frequency and time domain with a pair of operators called transform. So, therefore, a perfect example of a transform is Fourier transform, which converts a signal function into an integral of sine waves of variable frequency or sum, each of which symbolizes a frequency component. The so-called spectrum of frequency components is the frequency domain depiction of the signal. However, as the name implies, the inverse Fourier transform that we'll cover later on converts the frequency domain function back to the time function. This slide shows how we can visualize a signal in time domain and frequency domain. To go from time domain to frequency domain, we use Fourier transform. Now let us look at the introduction on Fourier transform. Fourier transform definition and application. As mentioned earlier, Fourier transform physically it will tell you the frequency components of your signals. Mathematically, it is often simpler to manipulate a function in the frequency domain, and we will look why. Most functions are composed of many different frequencies. Decomposing a function into its frequency components, for example, the expression of a musical chord in terms of the volumes and frequency of its constituent note. The Fourier transform has many wide applications such as image compression, filtering, and image analysis. Now let us look at Fourier transform of energy signal. The Fourier transform of a function xt is defined as this formula ft for Fourier transform of a signal xt, and the notation that we use is capital X with bracket of f refer to frequency equal integration of minus infinity to infinity xt e minus j 2 pi ft dt. According to Parseval's theorem, later in section 8.16, the amount of energy being used by a signal in different parts of the spectrum can be calculated. From Parseval's theorem, in order to obtain the energy of harmonics of the signal, the square the frequency representation in order to view the signal, meaning that we have to square the frequencies representation of the signal. Therefore, the energy spectral density of the signal is equivalent to the square of Fourier transform of the signal as given in the equation here. Epsilon f theta equal to Fourier transform square theta. Let us continue with the definition of Fourier transform. The definition requires the integral for all function for engineering well-behaved functions to converge and follow Dirichlet conditions as discussed earlier in Fourier series. So therefore it applies to Fourier transform as well. There are two. First, it has to be integrable over minus pi to pi. This is for finite. And suppose that the signal is a single value piecewise continuous. It has a finite number of jump discontinuities and must have a finite number of maxima and minima. Now let us look at the Fourier transform representation. If a signal in time domain is xt, the Fourier transform the signal is capital X bracket j omega in radian per second or capital X in bracket f if it in hertz. Fourier transform of a signal is a complex number having magnitude and angle. It can also be written in Cartesian form, which includes real and imaginary parts. For example, capital XF for Fourier transform of signal equal real of Fourier transform plus J imaginary of Fourier transform. In polar form, it includes magnitude and phase. For example, if we have the representation or the equation for Fourier transform of a signal, we can convert into the magnitude with angle of xj omega, or omega can be alternatively equivalent to 2 pi f. We will look more details of Fourier transform and its and examples in our next lecture. Thank you.